Hey folks, a very good evening. Could you please also confirm in the chat window? I have the chat window open on a different computer, basically my phone. Could you please confirm in the chat window if you're able to see my screen and if you can hear my voice, so that we can get started with the session in a couple of minutes. Could you please confirm that in the chat window? Is my audio clearly, is the volume sufficient? Let me just check here. I can increase it slightly. Okay, yeah, the screen is visible. Thank you folks, thank you for the confirmation. We'll get started. Oh, it's already 7 p.m. So let's get started anyway. Today is the digital logic design. This is the first live session for digital logic design. We have one more live session on the coming Friday, and we have a general live session on Saturday, as we informed you earlier this week, right, about the live sessions this week. So this is the first session. This is the syllabus, the basics of digital logic design, number systems, arithmetic operations, basics of Boolean expressions, logic gates, and Karnaugh maps, or K-maps for short. So some of the concepts here, like Boolean expressions, would have overlap with Boolean expressions and Boolean algebra in discrete mathematics also. So there will be some overlap in concepts because there is Boolean expressions and Boolean logic here. So there will be some overlap in problems also. Some of the problems that you see in this session, you could think of them to be problems in combinatorics or in Boolean algebra and things like that, right? Cool. So let's get started anyway. Since this is the first session, we'll start with the first problem. We'll start with some easy problems. As usual, I'll try and give you a detailed explanation after the problem is solved. I'm looking at the chat window, so please submit your answers there. Okay. So let's get started. Again, just one more thing. The questions that we are doing only for DLD, we have taken them from our practice tests. They're a small sample of questions from our practice tests because we redid the whole digital logic design content as students requested us. So let's get started. Somebody is asking for COA. I think we have already done it. Probably you missed it. They're available on our YouTube channel. Check out the previous sessions that we have done for COA. We have done 3 sessions for COA. So please check them. Cool. So let's get started here. Let's start with some easy problems. Here comes the first problem. Again, you can think of this problem from mathematics or from digital logic design. This problem is part of both. Okay, I request everyone to try to solve these problems because that's the most important task. As we are coming closer to the examination, I hope you have revised these concepts. And we'll start with some simple problems first. Then we'll go to more complex problems slowly. Not too complex, a little bit of medium. Okay, I see people submitting the answers. Okay, so we have, there are 2 basic options that people are picking. I can see the confusion also. It's a very common confusion. This is a simple problem. We are just warming up right now. We'll go to a few medium problems as we progress. Again, the confusion mostly is between options B and C. So be careful. I see some of you making a very silly mistake. Always draw diagrams, folks. The most important thing is to translate. Don't apply formulae. First, try to, whatever is the question, try to express it in a diagrammatic form. That way you can avoid lots of mistakes. I've mentioned this when we discussed COA also. For most subjects, okay, not just for GATE. In general, if you want to solve problems, one of the simplest strategies is draw diagrams because they'll help you understand what's happening visually. Okay, I see mostly answers B and C. Anyway, so let's get into the solution. The answer is actually B, and it's very straightforward. Let's draw the diagram. Oftentimes it's important. So what are the possible number of Boolean functions? So these outputs are Boolean with n ternary variables, right? So you have n ternary variables, right? So look at this. You have variable 1, variable 2, and variable n, right? So each of these can take 3 values, right? These are not binary variables. Each of them can take 3 values. right? So this can take 3 values, this can take 3 values, this can take 3 values. So if you try to think of it in terms of min terms, you will have 3 power n min terms, right? You'll have 3 power n min terms now. And your function, the Boolean the function that you have can only take 0 or 1 value. Think about it. See, any function, if you try to represent a function, if you try to represent a Boolean function in terms of a truth table, what I'm drawing here is a truth table, right? So for each of the, so if you think about it, you have 3 power n combinations here in terms of all the variable choices, and the function itself is Boolean. Remember the number of Boolean functions, which means the output has to be binary, right? We have solved similar problems in the course videos also, right? So those of you who are course participants, this is more or less straightforward, right? So if you see this, because this is Boolean, it will be 2 power 3 power n. Because look at this, here you can place only 2 possibilities, not 3 possibilities here. Okay, the output is binary, that's very important. Okay, the output, because it's a Boolean function, each variable is a ternary variable. So the answer is 2 power 3 power n. Again, some of you may say that this problem is actually a combinatorics problem, which is true, because functions is a concept in discrete mathematics also that we study, right? So this problem can be thought of as a problem in discrete mathematics, but we have also solved similar problems in the course videos of digital logic design, right? So this is an intersection of both. Cool. Let's go to the next problem. Okay, this is again, you can think of this problem also as a problem in logic or in digital logic design. So here comes the second question. Very simple question. Typically, you could be asked a question like this for 1 mark. Also, very simple question. We're starting off with some easy questions. So Nikhil has a question on how to use our course effectively. We have a video on the same topic on YouTube, on our YouTube channel. So Nikhil, just go to our YouTube channel, check it. If you cannot find it, just shoot an email, we'll forward the link to you. It's available on our YouTube channel. Again, this is a simple problem, fairly easy. Again, you can solve this very fast if you know the basic rules of Boolean algebra. Again, we are starting with a few easy problems to warm you up. Again, digital logic design is often easy in GATE. You don't get very hard questions from these topics. It's also fairly scoring if you know all the concepts. Again, just apply the basic logic, basic equations that you learnt in Boolean algebra. You can trivially solve this. Sorry, let me write it clearly. So this is one very, very popular equation in Boolean algebra or Boolean expressions, which is often used in many GATE questions. So even if you see a lot of previous year GATE questions, they are very much based on this expression. So x plus x dash y is x plus y. Okay, so if you know this, you just have to apply it here. Okay, so let me go ahead and answer the question. Most of you got it right. The answer is B. And again, this is a again, we have emphasized this formula extensively in the course videos also, because if you see a lot of previous year GATE questions, knowing this can simplify your problem. First and foremost, look at this. What is this? This whole part and this part are one and the same. This is a dash b dash plus a dash c dash, right? So if you just think about it, this whole thing, this is nothing but a dash into b dash plus c dash. So the moment you look at this, the first thing that should strike for you is as follows, right? So imagine if this is x, If this is x, this is nothing but x dash because there is a dash here. And you can think of this as y. Okay, the moment you see an expression, so the easiest way, if you know this is one very, very important formula in Boolean algebra as far as DLD gate questions are concerned, right? So if you think of this as x and this as y, this is nothing but x dash. This whole thing is nothing but x dash. So the moment you know this, you know that x plus x dash y is nothing but x plus y. As soon as you know that, so what is x now? X is nothing but a dash into b dash plus c dash, that is your x, plus y. What is your y? Y is a plus b, right? Very simple, very easy to simplify. If you know this single formula, it will help you a lot in gate. Again, you can apply this again. If you notice, one thing that you can notice here is, look at this. You have, so one thing that you can notice here, again you have a, the complement multiplied by something. You can apply the same formula again. Just that a is x now, this is x dash, this is y. You can reapply the same formula again. So when you apply the same formula again, what happens? You get a plus, this is your y, right? This is x dash, and this is y. Just apply the same formula again, right? So you get a plus b complement plus c complement plus b. Now one thing you can quickly recognize here is b plus b complement is 1, right? 1 plus anything is 1. So the answer is 1. So simplifying this it's extremely simple if you know how to apply this, and we just applied it twice. In literally 3-4 lines you can solve this, right? So you can actually solve this in about 30 seconds if you just know this. Again, please make a note of this if you already don't know this. This is one of the most important things. Okay. So somebody has a question, what should be the key takeaways after the test? Good question, Laksh, that you asked. So first thing here is, it will help you understand how well you are prepared with a given set of topics. That's one. Assessing that, how well are you able to solve and where you have gaps. Okay, again, most of the questions that we are asking in this first iteration are mostly easy and medium. We are not doing medium and hard questions now. So this should help you understand where your preparation stands, which topics you need to focus more on when you revise them. Okay, so that's the main takeaway of these interactive sessions. Okay, cool. So let's go to the third question now. Again, this problem can be thought of as a problem in functions and combinatorics, or this problem can be thought of as a problem in digital logic design. There is some overlap between concepts in discrete mathematics, functions, combinatorics, and digital logic design. So in GATE, they also like to give some questions in the intersection of these topics. So that's why we introduced some of these questions here. Again, you might have to use a calculator here, so feel free to do that. Please don't be in a hurry. Solve it carefully. Read the question carefully. Again, draw the diagram, folks. I just showed you, right? Draw the diagram or draw a table. Those will help you enormously. Again, please try to write the numeric answer. Think of it as a fill in the blank type question. So that will help you enormously. So you have three variables here. Some of you I think are getting confused. Let's assume you have three variables A, B, C. All these three are ternary variables. So how many functions we can construct? How many functions we can construct where the function cannot have, or function has at most 3 min terms. So we are constructing the function using minterms here. So please think of it as a fill in the blank question. Please enter the number, use a calculator if you have to. Because I see some of you writing mathematical expressions, please avoid that. Write it as a fill in the blank. Again, I see a wide set of answers. Again, this is also an easy question. Again, questions like these have been asked in the past for, again, sometimes you can think of them as DLD questions or discrete math questions, doesn't matter. But they are one type of popular questions, typically asked for 1 mark in GATE. Okay, I see a wide set of answers here. I think people are slightly getting confused with this. Okay. I'll anyway explain it. Let's give a few more seconds for everybody to take a shot at this problem. Then I'll explain it. Okay, so let's go into this. So first, given A, B, C, right? So you have 3 variables, A, B, C. Each variable can take 3 values. This can take 3 values, this can take 3 values, this can take 3 values. So how many minterms are possible first? Okay, how many minterms are possible? Because you have 3 variables, how many minterms are possible? There are 3 variables. Imagine if they were binary, you can have only 2 power 3 minterms if they are binary. But these are actually ternary, which means you have 3 power 3. So 3 into 3 into 3, which is 27 possible minterms here. So that's why it's important to draw this diagram of a truth table. Okay, imagine you're trying to construct a truth table, you're trying to construct the truth table or list down all the possibilities of ABC, right? That's what you first do, right, when you construct a truth table. But our function is not defined in terms of truth tables. Our function says that this function that we want to construct, so how many minterms do we have? We have a total of 27 minterms. So it says at most 3 minterms, right? So from 27, imagine if I want to construct an expression, if I want to construct a function with exactly 3 minterms, I just need to pick 3 out of these 27. So I need to choose 3 out of these 27 minterms, right? Those many functions I can construct if my function needs exactly 3 minterms. But it says at most 3 minterms. So this is 3 minterms. This is 2 minterms. This is 2 minterms. This is 1 minterm. This is 0 minterms because it says at most 3 minterms. So we could have 3 minterms, 2 minterms, 1 minterm or 0 minterm, right? So if you simplify this, again, some of you wrote this expression also. You might have to use a calculator for this just for speed and to avoid silly mistakes. The answer is 3304, right? Many of you got this, happy about it. Again, this is a simple problem, right? If you know discrete math, you can solve this even without knowing much of digital logic design, right? And there is some overlap between both of them. Okay, so let's go to a slightly more interesting problem now. Again, some terminology that you have to know here and some simplification techniques that you need to know. Again, please read the question carefully. This is slightly lengthy problem, but you can also solve this fast by eliminating options. Again, this could be slightly lengthy, so please take your time. It's okay to take time. This question is not hard. You just have to know what is the concept of essential prime implicants, and you should be able to carefully solve them. That's all. Yeah, I think some of you may not know what is an essential prime implicant, but it's an important concept to learn. So you could learn that terminology after the session is over, if you don't know that term. Anyway, I'll explain it here also when I explain the solution. This is a standard term that you find in most textbooks. Somebody says, should we use a K-map in order to solve this problem? Yes. Yes. Essential prime implicants is a concept related to K-maps. Yes. Yes. You have to draw multiple K-maps to answer this question as a hint. I'm just waiting for a few more seconds because people could be solving this problem. This is just lengthy. This is not hard. Okay, let me try to answer this. So I'll explain what is the concept of an EPI or essential prime implicant while I explain the solution, right? So let's take this set first. So first let's draw the K-map corresponding to it, right? So first I'm looking at this first, okay? So let's assume I have Z and I have XY. This is 0, 1, this is 0, 0, 0, 1, 1, 1, 1, 0. Okay, let me start filling it. So I have XY first. XY means this will be 1, this will be 1. Okay, then we have YZ. So where is Y equals to 1? Y equals to 1 here, Z equals to 1 here. So YZ is these two cells, right? Similarly, what do we have? We have XZ. So X equals to 1 is basically this 4 and Z equals to 1. So this and this, right? Then you have XY dash, which means X should be 1 and Y should be 0. So X is 1, Y is 0. So these two cells, okay? So now if you notice, if I'm trying to simplify this whole thing, I can create a box of size 4, or I can create, this is called a prime implicant. If you group all of them and if you write the expression for it, that's called a prime implicant. Okay. So here you're given these 4 prime implicants. Okay. Each of them you can think of it as a prime implicant because they correspond to a box. Okay. So if I were to simplify this, I'll group these 4, right, into one prime implicant. I'll group these 2 into second prime implicant. Okay. So an essential prime implicant is something that is essential or that needs to be there in the final expression. You can't simplify it any further. Here you have 4 prime, look at this, here you have 4 prime implicants, or you have 4 product terms, each corresponding to a prime implicant of sorts, right? But if you notice, instead of these 4, we can simplify it. Imagine we have these 4, corresponding to these 4, what is the expression that we can write? Look at this. We can say what is corresponding to these 4. So your Z can be anything, right? So what about your X? Your X is 1, right? Your Y can be anything. So corresponding to this 4 box, your expression is X. Corresponding to this 2 box, what is it? Z is 1, so you will have Z. What about X? X is changing, Y equals to 1. So corresponding to this 2 box, you have X and YZ. So while there are 4 product terms here, they are not essential prime implicant set, because if I try to minimize them, my essential prime implicant set actually consists of X comma YZ, because they both are essential when I have the most simplified form. Okay, a prime implicant corresponds to a box that you draw, intuitively speaking. An essential prime implicant is something that you can't merge with others, that you can't replace. It's essential to the simplified form. Okay, I'm just trying to give you an intuitive feel of it. So this set certainly does not contain only essential prime implicants, right? Because we are able to simplify it further. Now what about this? So 1 cannot be in the answer. Since 1 cannot be in the answer, this can be eliminated, this can be eliminated. Let's start eliminating options. Okay, what about 2? What do you have in 2? So let's draw the K-map corresponding to this also. So right, so you have Z, XY, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Just like the way we have drawn here, we can also draw for this, right? So if you draw for it, you will get this K-map. So if your prime implicants are X dash, X, Y, Z, X, Z dash, Y dash, Z dash, the final ones you will get in these places. Okay, you can verify that. I've shown it to you here. In the interest of time, I'm just drawing it here. Now, if you notice, one more thing that you should notice here quickly is, can we simplify this? Yes, one way to simplify is to create this box of 4 and this box of 4, right? So what does this box of 4 corresponds to? It corresponds to Z equals to 0. So this is Z dash. Now what does this box of 4 correspond to? This box of 4 corresponds to your Z could be 0 or 1. Your X could be, your X is always 0 here. So X dash, right? So while you have you have 3 product terms here, right? If I actually place the ones corresponding to these product terms, the essential prime implicants are Z dash and X dash, not these 3. Okay, so these are also not a prime implicant set because I can further simplify them by grouping them. So they are prime implicants, but they are just not essential prime implicants because I can simplify them further. So 2 also can't be the answer. So you eliminate this option also. So obviously option is C, right? So those of you who may not have heard of this term, just Google search for it. You can find it on Wikipedia. You'll find it on lots of blogs. You'll also find it on your standard textbooks. Okay. So each of these is called a prime implicant, or each of these product terms corresponds to a prime implicant. You can think of prime implicant as a box. That's one simple visual way of thinking about it. Essential prime implicants cannot be further simplified, right? You can't go anything below that. That's the whole concept. Cool. So this is a slightly lengthy question, but a easy question. If you know the concept of EPIs and if you know how to draw K-maps, you can solve this. Cool. Let's go to the next question now. Okay, this is a good question. This is about number representation, floating point number representation. Please read the question carefully. Again, this is very, very prone to silly mistakes. So please be very, very careful answering this. So Vikram has a question. Is it too late for a third year student to start his preparation? Not at all, actually. We have seen people who started their preparation even in early September last year and we have gotten good ranks. So since you're in third year, start your preparation now. If you get a good rank, very good. In case you don't, that preparation will always help you for the next year, right? So if you're disciplined, of course, you'll have to put more effort than somebody who started earlier, but it is very possible to even crack GATE in February, starting from September, even mid-September. Again, please be very, very careful. There is no hurry. Take your time. Draw the diagrams, folks. You know how to draw the diagram of the sign bit, exponent bits, mantissa bits. Draw it and think from the diagram perspective. If you want, I'll draw it for you without putting the answer numbers. Right? So this is your diagram, right? This is your sign bit. This is your exponent bits. This is your mantissa bits. Right? So start from here. This whole thing is 16 bits, remember. right? This whole thing is 16 bits. Now start drawing the diagram and start filling in the bits. That way you'll avoid mistakes. I see people putting in the answers already. Please don't be in a hurry. Think through this. This is slightly tricky problem. If you're not careful, you'll make mistakes. Again, somebody is asking for a hint. I want you to figure it out. I'll tell the solution, Amit, little later, but I want you to figure it out. The largest number should always be a positive number, right? Obvious. Again, please take your time, draw this diagram and start filling in the details from here. You have a sign bit. You have a bunch of exponent bits. Again, some of these, I think this concept is freely accessible to everyone. I think the videos on how to actually represent using Mantissa, using IEEE format, I think those videos are publicly available for everyone. So in case you have some doubts, you can always check out the freely available videos, even if you're not a course registered student. If you're a course registered student, anyway, you have access to all of this. Yeah, this is one of the concepts where students mess up a lot. That's why we kept it open for everyone to read. Okay, people are all around the place. Somebody says 2, somebody says 3, somebody says 4. Okay. Again, those of you who have watched the course videos, we used this, right? The number of bits in exponent, we wrote it as lowercase e in the course videos. So if that might help you, please try to use that. Again, this is XS64. It says clearly, no, implicit representation. It says clearly implicit here. This is an implicit representation. Again, those of you who are not comfortable with this, the videos on this are publicly available. Please check it after this session. Okay, so let me get into the solution, right? So let's go step by step. Again, I'll try to use the same notation that I've used in the course videos so that people who have gone through those videos can easily understand this. So we have a 16-bit register. M denotes Mantissa, cool. So it's all implicit representation, understood. It's XS64, right? So which means, look at this. So one thing that, so this is basically your bias in your representation, right? I use the same terminology in the course videos also. So how do you represent bias? So this 64 is basically a bias. So you're biasing your exponent with 64, right? So your bias is represented as 2 power e minus 1, where e is the number of bits in the exponent. So first, this we know is only 1 bit. That part we know, right? This is a signed bit. This signed bit will be 0 because the largest number has to be a positive number, and all the 4 options given are also positive numbers. Now the total bits are 16, we know that. If we can somehow figure out the number of bits for the exponent, we can automatically obtain the number of bits in Mantissa, and then we can solve the problem. So the question here is how do we obtain the number of, so let's assume e is the number of bits for the exponent. So one thing that we know, that if the bias is 64, because it's an XS64 format, if the bias is, because this is biased exponent representation, right? Because it is 64, we know bias is always equals to 2 power e minus 1, and the bias here is 64. So 64 is 2 power e minus 1. So what does that imply? That implies e equals to, so 2 power 6 is 64. So e minus 1 is 6. So e equals to 7. So which means this is 7 bits. So if this is 7 bits, this whole thing is 8 bits. Straightforward, right? Number one. Okay, so now we got the basics. So that's the first step in determining. So first, again, draw this diagram so that you can fill in those details. Okay, number one. Number two is, now the question here is, what is the largest value that you can represent? Okay, in base 10, that's the question. It's all binary. So if all of the largest number that you can fill here is ones, 4, 5, 6, 7 ones. The largest number here is 8 ones. And this is an implicit representation. So if this is what you have in binary, how do you represent this in, how do you write it mathematically? Because this is implicit representation, 1 dot 8 ones, 1 1 1 1 1 1 1 1 into, right, 2 power whatever you have in exponent. Look at this, whatever you have in exponent minus bias. So whatever you have in exponent minus bias is 64. Okay, now what is there in E? Look at this, all ones. There are 7 ones here. If you have 7 ones, what is it equal to? It is equal to 2 power 7 minus 1, which is 127. So this is nothing but 2 power 127 minus 64, right? 2 power 127 minus 64. And what is this? This is nothing but 63, right? So this is nothing but 2 power 63. This is what you have. Now notice that all these are given in 2 power something, right? Which means, look at this, you are given 2 power 55, 64, 64, 55, etc. Now if you notice, if I move this dot here, because there is no decimal values here, all of them are integer. So if I move this dot by 8 digits, sorry, by 8 places, what do I get? I get 9 ones, right? 5 ones, 4 ones into 2 power, because I'm moving it by 8 places here, 63 minus 8, which is 55. So this is what you have. This is in base 2, obviously. So this is what? 5 nines. What is 5 nines? 5 nines is 2 power 9 minus 1, which is 511. So what do you have? You have 511 into 2 power 55. So the answer is 4. Again, the question is slightly intricate because you are not given explicitly the number of bits that you have in the exponent part of your 16-bit representation. That's what is not given. But given that the bias is 64, because it's a biased exponent representation, right? Given that the bias is 64 and we know bias equals to 2 power e minus 1, and why is this so? That's something that we described in the course videos. Why do we choose this? Why do we choose the bias to be equal to 2 power e minus 1? We actually argue why this is a good fit in the course videos, right? So please try to check that because they're publicly available. But let's go to the, again, for most questions, please draw the diagrams. That will help you enormously. Okay, so let's go to the next question now. This is an easy question. Just be careful here. While this is easy, it's very easy to make a silly mistake also here. Yeah, we are placing a few easy questions, then few medium questions, and so on and so forth. I think this question is easy, sure. I think the next question is also easy. Then we have 2 medium questions. Okay, I see people putting in the answer. Okay, let me see this. Again, please remember the 2 numbers are represented in 2's complement form. Again, please be careful here. I see some of you making silly mistakes. So please be little careful. Okay, I see people putting in options 2, 3, and 4. Again, this is an easy problem. If you know the 2's complement representation of Boolean numbers, this is fairly straightforward. Okay, I see a bunch of you putting in the answers. The answer is 2, obviously. So let me go ahead and explain the solution, right? This is your P, right? This is your P. This is in 2's complement form. Notice that the first digit here is my 1, which implies that this is a negative number, first and foremost. Then from 2's complement, let's get 1's complement, which means subtract 1 from this. Then you get 1's complement, right? What is 1's complement of this? 1's complement is 111, 0, 11, 00. This is your 1's complement. From 1's complement, let's get the regular number. Okay, so what do you have here? 000, 1, 00, 11. All right, yes, this is what you have. Now, what is this equivalent in decimal? This is 2 power 0, which is 1. This is 2 power 1, 2, 4, 8, 16. So 16, 17, 18, 19. So this represents minus 19. Okay, P represents minus 19. What about Q? Again, this is, look at this, the first bit here is 1. So it's a negative number, that we understand. Subtract 1 from this to get the 1's complement. Okay, so if you subtract 1 from this, what do you get? You get 111, 00, 101. Because from 10, if you subtract 1, you get 01. Right? This is your 1's complement. From this, let's get the regular number, right? So 000, 11, 010. Okay, so what is this? This is 2 power 0, this is 2 power 1, 2 power 2, 2 power 3 is 8, then 16. So 16 plus 8 is 24, plus 2 is 26. So this number here is minus 26 in decimal. So it says Q is subtracted from P. So minus 19 minus 26. Let's just do this math in decimal, right? So we know that this is equal to plus 7, right? And we know what is the representation of 7, right? The representation of 7 is this. That's all is the answer, right? This is one of the ways of solving it. Okay, so you convert your P into decimal because we know decimal arithmetic much better, right? So just recognize that it's in a signed 2's complement form. So just get that number, get the number, do all of our arithmetic in decimal because less chances of doing silly mistakes, right? That's it. Cool. So let's go to the next question. Somebody says, is it advisable to convert the number to decimal? Yes. Again, I prefer doing arithmetic in decimal so that there are less silly mistakes. In binary, I often do silly mistakes myself, right? So that's the important part here. Cool. So let's get into this now. The next question here is, again, this is a very straightforward question here. This is about, this is just checking. So somebody is talking about question 5. We did not say it's IEEE format, right? Tanay, you are assuming that it's IEEE format. We never said it's IEEE format. So that's an assumption that you made. Okay. So coming to question 7, this is a very simple question. Let's solve this. If you just know what is XS3, BCD, it's done. Again, for the previous question, there are many ways of solving it. I am trying to show you a method that I follow to avoid silly mistakes. You can solve it in other ways also. Again, this is a trivial question actually. You could be asked this question for about 1 mark. If you know what is XS3, if you know what is BCD, this is straightforward. This is a simple question. Okay, yeah, most of you are getting it right. Very straightforward. Look at this. It's binary coded decimal, right? So it's BCD. It's also following XS3, right? If it's BCD, you represent each number using the binary. You don't convert 597 into binary. You convert each digit into each decimal digit into binary. That's what BCD stands for. It's also XS3, which means 5, you have to add 3, then you will get 8. So what is 8 represented as? 8 is represented as 1000, right? Similarly, 9 plus 3 represented as 12. So what is 12? 12 is 1100. 7 plus 3 is 10. So 10 is 1010. So where do we have this? This is 1000. So this is 1000. This is 1100. Okay, so 1010. Option A is the right option. That's it. You just have to know what BCD means. BCD means each digit is converted into binary and not the whole thing converted into binary equivalent. XS3 means each of them needs to be added with 3. That's it. If you know these two concepts, it's a trivial question. Okay, let's go to more interesting. We have 2 more questions, more interesting questions. Here is a good one. I enjoyed solving this. This is not hard, but this was fun solving it. The last 2 questions are fun. So let me put it here. So this is this multiplied by this multiplied by this, in case you have a doubt. You will not get extra marks for speed. So it's important to get the answer correct rather than fast. Again, just be careful here. Draw the K-map. The expression given is POS. So be careful with it. This is not hard. This is simple. If you're careful with it, it's actually, you can do it in like under a minute. Again, most K-map questions are easy. I have one more question for you after this. If you know how to use K-maps, it's a very simple concept. Most problems will be easy if you know how to use it and you don't make silly mistakes. Okay, we'll wait for a few more seconds for everyone to finish it. Okay, most of you got it right. So first, this is POS expression, right? So let's write what is it in POS, right? So what is it? It's a product of what? Okay, let's write that down. So when you're writing POS, very common mistake is people mess up POS SOP representation. In POS, this is 0, this is 1, and this is 1, right? So this corresponds to 3. Okay, that's a common mistake that people do. In POS, this should be 0. This is 1, this is 0. So this is POS term 2, right? What about this? This is 0, 0, 1. Okay, so this is POS term 1. So this whole expression is nothing but this. And we know how to convert from POS to SOP, right? POS to SOP is nothing but whatever is not here. So it is 0, 4, 5, 6, 7. Now the question says, what is a simplified SOP form of it? Again, I always prefer drawing my K-maps in SOP because I'm just used to it. Lesser chance of errors. Okay, so let's draw this down now. Okay, so you have PQR. So you have P here, QR here, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Okay, you have 0, so which means here. Then you have 4, 4 is 1, 0, 0. Then you have 5, 5 is this, 6 is this, 7 is this, right? So this is what you have. Now this can be easily simplified. We know that, right? So there is a prime implicant of size 4 here. There is a prime implicant of size 2 here, or a box of size 2 if you want to think about it simply, right? So what is this box? This box is basically P. What about this box? This box is Q dash R dash, right? So which option is correct? P plus. So the answer is P plus Q dash R dash. So option B is the right option. Very simple. So don't worry that you're given a POS. Just make sure that you get the POS expression correct, and then you can get this and you can get this. Again, Nihal has a good question. He says, can we solve it using distributive law? Yes, you can. There are many ways of solving it. K-map is just one of the ways to simplify it, right? And also a very powerful visual way. It's actually a very good graphical tool. Of course, you are always free to apply distributive law using simplification rules. You can solve it like that also. Nothing stops you from that. But K-maps are much more easy to work with. They avoid silly mistakes. There are many ways. Again, as somebody rightly pointed out, you have this term, same term you have here also, right? So there are many ways of solving this problem. No doubts about it. Cool. So let's get into the next question. This was a good question. Again, this question is easy if you know how to solve it. You just have to be patient and careful. Again, these bits here, just to be clear here, these bits are YZ variables. These bits are WX variables. I just wanted to, so these are YZ are here, WX are here. Okay, in case D is, don't care. Just in case you have a doubt. Again, this could be slightly lengthy, but that's okay. Take your time, think through it carefully. So these are typically called as variable entrant maps. We discuss about them in the course videos also. Amit asks, do we get VEM questions in GATE? Again, you could get it, right? So we always want to be on the safer side and cover. That's why we covered lots of examples of VEM also in the course videos. Just to be careful. That's why we've added a question also here, just to make sure that you know the concept in case it is asked. It's better to be on the safer side. It's okay to prepare a couple of more concepts than being sorry in the exam. There are some simple steps that you have to follow for VEMs. If you follow that, the problem is straightforward. Again, DLD is very scoring if you know the basic concepts. Again, take your time. This could take a little more time than normal. That's okay. Again, slightly lengthy questions like this are often asked for 2 marks. It's okay, take your time. Again, there are basically 3 simple steps to simplify VEMs or variable entrant maps. Cool, I see most of you got the right answer. The right answer is 2, option 2 or option B. For those of you who don't know how to solve it, let me explain it, right? So whenever you have variables here, look at this. This is a simple K-map except that you have variables here. That's why it's called a variable entrant K-map or variable entrant map. When you have this, the first step that you have to do is ignore all the variables, make all the variables 0. Don't care, sir, D. First thing is just ignore, first step is just ignore all the variables, make all variables 0. Wherever you have a variable, any variable or any expression, anything, just make it 0 first. Okay. Then what are you left with? You are just left with this. Look at this, there are only 2 ones. Okay. But these are don't cares, right? So you can always group these don't cares and create a prime implicant box of size 4. Right? So what does this give you? Look at this. So D could be anything, right? You can't create a prime implicant box of size 8 here. You can't create this because these are zeros, right? You can't create this box also because there are zeros here and there is a 0 here. So this is the best box that you can create. Now, okay. So what is this? What do we have here? Let's look at each of the terms, right? So W is 1 here, right? In this box, W is 1. X can be 1 or 0. What about Y? Y can be 0 or 1, but Z equals to 1. So this box gives us WZ. Okay, so let's write down WZ here. Okay, that's the first part. So this can't be the answer, either this or this. You could also have none of the above. So we have to be careful here. So first step is all variables, make them 0 and try to get a answer first. Okay, try to get an expression like this. Second, make the variable equals to, make one of the variables equals to 1. Okay, so let's assume V equals to 1. Then V complement becomes 0. This V is 1. This V complement is 0. Do we have V complement anywhere? Nothing there, nowhere else. So what are we doing here? We are making V equals to 1. So in the expression, multiply with V, whatever you get now. Now, if you notice, these are don't cares. So you can always group this whole thing, this whole prime implicant box of size 8. This box of size 8. In this box of size 8, what is commonality here? So if you notice, only Z equals to 1 here. So Z, Y is changing, W is changing, X is changing between 0 and 1. So this can be represented as Z. So whatever you get, you multiply with V. Because we used V equals to 1. Remember, we used V equals to 1. That's why I wrote V here. Okay, plus. Okay. Next, make V equals to 0. That's another possibility, right? If you make V equals to 0, V complement becomes 1, this becomes 0, this becomes 0, this becomes 1. So you write V complement multiplied by something. Okay. So again, this term is the same as this term. So these two terms, or it could be none of the above. Whenever you have none of the above, you have to be more careful. Okay. Now, so how do you now group these things now? Look at this. What all do you have? So one common mistake that people do is grouping here. Look at this. You have this one, this don't care, this don't care, this don't care. You can combine these 4. If these don't cares are treated as ones, this one, this one, this one, if you treat it as don't care, this one as don't care, then these 2 ones are covered, right? So what do you get there? What do you get there now? So if you cover these 2 ones, so if you make these 2 ones, what do you get? You get what is the commonality in these 4? You get let's see. So what is x here? X is 0 here, x is also 0 here, so x dash. Then what else do you have? You have, look at z. Z is 0 here, z is 0 here. Look at this, z is 0 here, z is 0 here, right? So you have z also. These ones were already covered in the previous expressions, right? Remember, these ones, we covered it in the very first, in this expression itself, we covered these two ones. So we don't have to worry about it. So the final expression that you get is wz plus zv plus v dash x dash. One second, why is it z dash? One second, did I mix? Oh yeah, it should be z dash. I'm sorry, because z equals to 0 here. I'm sorry. So z equals to 0, so it should be z dash. So option 2 is the right option here. Again, the reason we covered VEMs is because it's good to know this concept in case there is a question that's asked in this. Okay, so cool. So this was the first session. So we will conduct the next session on Friday for digital logic design with rest of the concepts. So you will have combinatorial circuits, you will have sequential circuits, counters, all of those concepts in the next session on Friday. We also have a general session in we also have a general session on Saturday, right? So we'll look into that. Again, some of these concepts have been explained in a lot more detail in the course videos. Let me just show it to you because that could help you. So some of you, again, there are a bunch of free videos that we redid. So there are a bunch of subjects that we redid. Let me just go here, go to digital logic design. Yeah, so again, the number systems, so anything which has this I symbol is publicly available even to non-registered students. So this whole chapter with Booth's algorithm, with IEEE representation, floating point using normalized mantissa, all these videos are publicly available. So the first 2 chapters are publicly available. The first unit itself is publicly available. So please check that, and we will announce the next subject after DLD probably on Friday or Saturday when we have the general session. Okay. Thank you very much, folks. Thank you for joining today, and see you on the coming Friday. Bye-bye.